Since the earliest civilization and before, mankind has pursued a study of the stars. The first optical aid to this study didn't come about until the invention of the telescope in the early 17th century. While the telescope collected and focused light, there remained no way to actually record an image. This was placed in our grasp in the 1870s, when the invention of photography allowed astronomers to preserve images on film. With this technique, light from faint objects is focused on light-sensitive chemicals to slowly build up an image. This is the most common means of preservation to date. The last decade has seen a tremendous refinement of television and digital electronics. Now, the technique of video astronomy is materializing into a legitimate form of image analysis. The three-college observatory you're now seeing is located in central North Carolina. There, astronomers will observe the sky using all three of these aids: a 32-inch telescope, photographic facilities, and a digital video system. This unique video system was constructed by the Quantex Corporation and consists of three main parts. The first is the camera. Unlike other television cameras, this one is designed to function under low light conditions. The camera is an ISIT, which stands for Intensified Silicon Intensified Target. This means that the incoming light is electronically intensified by this device before it strikes the pickup tube. The pickup tube is the optically sensitive eye of the camera that converts light into electrical impulses. This signal is then passed to the second element of the system, the camera control unit. This controls and regulates the TV signal before it reaches the third and final element, the DS-12. This unit changes the continuously varying analog video signal to digital form. The final digital picture is made of little blocks of information called pixels, which stands for picture element. This means that a pixel is the smallest unit of the entire image, much in the same way that a single block is the smallest unit of this graph paper. A whole picture can be created by the shading of these small blocks. This is the incoming analog signal. And this is what it looks like after digitization. The analog signal is continuously converted to digital at a speed that produces 2 million new pixels every second. This is a television grayscale that shows 9 different shades of gray. The DS-12 is able to distinguish 63 levels of gray. But the human eye cannot distinguish light gradations this finely, and this is where a microcomputer is essential. The microcomputer has been programmed to translate these 63 levels of gray into an alphabetical code. The lower levels of gray are represented by the lowercase alphabet A to Z, and the higher levels of gray are represented by the uppercase alphabet characters A to Z and the numbers. This allows more precise image analysis. In addition, an entire image can be stored on magnetic floppy disk. This disk contains part of the constellation Cygnus. It's a permanent record of the sky and is available anytime to the computer. The DS-12 has many other features that increase its value as an observational aid. We can amplify the overall picture with the sensor gain, much in the same way turning up a volume control makes the sound louder. You are seeing and hearing noise produced when high gains are used. The noise is undesirable because it obscures the desired signal. To eliminate this problem, the DS-12 has an averaging mode. Since video noise is random, this average function allows us to suppress the noise and enhance the unchanging portion of the picture. This scene is illuminated solely by one candle placed 90 centimeters away. The light flickers and is uneven. When we use the averaging mode progressively, increasing the time over which the video is averaged, the light becomes continuous and is evened out. Another video enhancement feature is the summing mode. In this mode, successive images are added mathematically to increase the brightness of each pixel. This way, the dim areas of the picture can be made bright enough to view. The last important image enhancement feature is the integrate mode. This mode stops the scanning beam from reaching the pickup tube for a few fractions of a second. The result is that a faint image has time to store up the effect of light on the pickup tube before it's sent to the DS-12. This is similar to increasing the exposure time to allow more light to gather on a piece of film. In addition, the DS-12 auto sequencer can be programmed to allow the user to operate these three modes sequentially. In order to demonstrate the capacities of the system, we will now view some actual stellar images enhanced through video processing.